Hello and welcome to another lecture in the course. So we're still looking at Laplace transforms. So this is part 2 of section 6.1 in the book, and you can get the book over here at this URL. Here you can browse it on the web, get a PDF, get a an inexpensive paperback. All right. So still looking at Laplace transforms, and as we said at the end of last lecture, not all functions have Laplace transforms, right? But many do. Actually, uh, most of the stuff that comes up in applications of this stuff, you have absolutely no trouble with, right? So most of the time, you're going to be fine. You just want things that you want things that are going to be defined for all time, and or for all positive time, and you don't want them to grow too fast. You don't want them to blow up somewhere, essentially. So so how we're gonna describe this? Well, so we're gonna say, so this is gonna be the blow up at infinity. We also don't want any blow ups at some finite time, but I guess the main thing is infinity. So we're gonna talk about exponential order as time goes to infinity, and that means that the function in absolute value is no bigger than m times the e to the ct for some c and some m, and at least for sufficiently large t. So we don't really care what happens for some finite time. We don't really care about what happens as t goes off to infinity. So for large enough t, we want f to be no worse than this. So it can go to infinity. We're allowing to go to infinity as t goes to infinity, but it shouldn't go there too fast, or minus infinity, or could oscillate or whatever. But the size of it shouldn't go to infinity too fast, right? So you want this estimate over here, at least for large enough t. And so m and c are some constants. You're allowed to pick those constants. So if you can pick them such that this is true, then we say that it's exponential order as t goes to infinity. So one way to check this condition is to compute this limit, right? So if we basically divide by e to the ct, right? And if you compute this limit, and if you get something finite, or well, actually, usually it's going to be zero. You can always make c just a little bit larger, and it's going to be zero. So if you, for some c, if you get that this limit is finite, or again, as I said, usually zero, then f is of exponential order, right? So you could just try to compute this limit. That basically says that e to the ct, if we're doing a race between f and e to the ct, e to the ct wins, right? And so f is no worse than e to the ct, right? That's basically what this says. Now, a sum of any two exponential order functions is of exponential order. Any linear combination. So every polynomial is of exponential order, for example. So even though it grows as t goes to infinity, like let's say just some function t, right, that grows as t goes to infinity, that's fine. So it's exponential order, just like e to the t, right, is of exponential order, or e to the at for any a, right? Those are all exponential order. E to the t squared is not of exponential order. That grows too fast. You would find that if you compute this limit, it always goes off to infinity. So it's never finite, and definitely never zero. So e to the t squared grows really fast, much faster than e to the at for any t. Like e to the million t, still e to the t squared grows faster as t becomes very large, right? That's the point. As t goes to infinity. All right. So here's sort of the main existence statement for Laplace, and is really we're only interested in exponential order. So if you have a continuous function, defined on the interval from 0 to infinity, and it's of exponential order for some constant c, then the Laplace transform is defined for all s bigger than that c, right? So once you check exponential order, then you know that you can do Laplace transform. And continuous actually good enough if there's some jumpy discontinuities, but we don't want discontinuities that like 1 over t would have or something like that, right? Those sort of things would be bad. But if it jumps, it's fine. So that's not too bad. We just don't want it to go off to infinity. But so, like for example, the heavy side function has a jump discontinuity. We are fine with those kinds of things. And the theorem is not difficult to see. So suppose that we have this inequality for all, well, let's just say t equals bigger to 0 for simplicity. Now, if s is bigger than c, that means that s minus c is bigger than 0, then we use comparison theorem for calculus, right? The integral over here, the integral for the Laplace transform exists if this integral exists, and that exists because, well, you just write it out, right? It's this guy, and we know how to compute this thing. We did that last time, right? I mean, it's this m over s minus c, right? So as long as s minus c is positive, so as long as s is bigger than c, yeah, then everything is fine. This thing exists, and therefore this thing exists. All right. Now, if f is of exponential order, there's one more thing that this computation says. It says that, well, basically this thing goes to 0, and that's kind of that's the worst that your function can be, right? So this thing goes to 0 as s goes to infinity. So your the Laplace transform of f for any exponential order function is actually going to go to 0 as s goes to infinity. And that's also sometimes useful. We'll see how that comes up a little later. All right. So now the next theorem, so we have existence, we have uniqueness, right? So suppose that we have two functions that are continuous and exponential order, and suppose that their Laplace transforms are equal for large enough c. So somewhere, far enough out, they are actually have the same Laplace transform. Then they're actually the same function. Well, at least for t bigger than or equal to 0. And you can't say anything about less than 0 because Laplace transform is not defined for t less than 0. All right, so as I said just before, it's again holds for piecewise continuous functions. As long as you have just jump discontinuities, everything's fine. One thing that you're not going to get with the uniqueness is that you're not going to get that they necessarily have to be equal, at the singularities, but at the jumps. But that's just this discrete set of points. We don't really care about that. Outside of those discontinuities, they're going to be equal. Now, the reason why I stated it for continuous functions is to make the statements of the terms, be simple enough, rather than make them so complicated, right? So this is kind of a remark that you could still have piecewise continuous. That's fine. You just don't want things going off to, like, you don't want something like 1 over t. Don't want that, or tangent of t, right? Those things are bad. All right. So now the uniqueness, it says that it makes sense to find the inverse, because there's really only one function who has a certain, a certain Laplace transform, right? So given the Laplace transform, I can find the unique function that gets me that Laplace transform, right? So we can define the inverse Laplace transform. So if capital F is the Laplace transform of little f, then we have that the inverse Laplace transform of capital F is little f, right? That's the definition, right? So knowing that, if I apply the formula, with f, I get capital F, that says that, the inverse transform of capital F is little f. Now, there is an integral formula for the inverse, but it's complicated. It requires complex analysis. So we don't really, we're not going to look at it definitely, and we don't really worry about it. Now, the thing is that we're mostly not even worrying about the integral formula for the forward. We're mostly using the table, right? I mean, we know that there is a formula. It's useful sometimes, but we're not really too worried about it for computations. For computations, we are just looking at the table and using linearity, really, right? So for the inverse, we'll just look at the table. We're not gonna worry about trying to compute this in some other way. All right. So for example, via the table, if you look at the table, the Laplace transform of e to the minus t is 1 over s plus 1, right? So what that says is that the inverse Laplace transform of 1 over s plus 1 is e to the minus t, right? That's the way that we're going to be applying it, really. And the inverse is also linear, right? If I have a times capital F and b times capital G, where capital F and capital G are the Laplace transform of something, right? Then a times, well, this would be maybe the little f, and this would be maybe the little g, right? A times little f plus b times little g, right? So again, I can just use linearity. If I write it as a sum of things, I can apply the inverse Laplace transform to each term in the sum, right? So divide and conquer, right? And of course, that means I can also pull out constants, right? All right, so let's see an example of this. So let's find the inverse Laplace transform of this guy over here. So what we're going to do is, well, this doesn't look like anything in the table. So we're going to split it up with partial fractions. So we look at this, and we factor the denominator. So s squared plus 1 can't factor anymore, at least not with real numbers. So we're going to leave it like that. But partial fractions, we can take this, which is a proper rational function, and we know that we can write it like this for some a, b, and c, right? So for the s, we have just a over s. For the s squared plus 1, it's irreducible. Quadratic, well, we have to put some linear term on top, or affine linear, and we don't quite know what b and c are yet, right? But if you just remember, recall from calculus, I mean, how do you do this? I mean, there's a bunch of ways to figure out what a, b, and c are. I mean, basically, we're just trying to find constant a, b, and c such that these things are equal, right? They're all the same thing. So what you could do is you could just clear denominators. You could just multiply by s times s squared plus 1. I mean, that's the easiest way to do it. I mean, there's sometimes some shortcuts, but this is this will always work. Just clear denominators. You get so you get the numerator here is going to be, well, over here. It's not equal to this numerator, but for example, over here, if I have a over s, I multiply it by s times s squared plus 1. The s will cancel, and I get a times s squared plus 1. Similarly, over here, I get, well, the s squared plus 1 will cancel. I get s times bs plus c. And now you just expand this, right? Figure out how many s squareds you have. For example, you have as squared out here, and then you have bs squared out here. And so a plus b is going to have to be 1 because there's 1s squared out here, right? So again, so expand, equate coefficients, and you get these things. So the s squared coefficient is going to be a plus b on the right hand side. The s coefficient is going to be c right? There's nothing out of here, and out of here there's only c times s, right? And there's one s here. Yeah, so I actually already know that c has to be 1. Then for constants, there's no constants out of here. For here, I just get a, right? So a has to be 1, right? So if a is 1, right, then b has to be 0, right? Because if a is 1, a plus b is 1, so b has to be 0. Okay, so a is 1, b is 0, c is 1. We plug that into here, and we get that whatever this capital F is, I can write it like this, right? 1 over s plus 1 over s squared plus 1. And so by linearity, say if we're taking the inverse transform over here, well, it's the inverse transform of 1 over s plus the inverse transform of 1 over s squared plus 1. Inverse transform of 1 over s is 1. Inverse transform of 1 over s squared plus 1 is sine of t. All right, good. All right, now, a useful property, useful in a number of ways, but for example, it's going to be useful in some inverse transforms, is the shifting property, and it just really just follows from the formula. You can just plug that into the formula, and you get this, right? So it's if I multiply a function of t with e to the minus at, that's just like taking the inverse transform of little f and plugging in, instead of plugging in s, we plug in s plus a, right? And it's useful here for us at this point is to think of it in reverse. So if we have f of s plus a, then, and if we can invert f, capital F, right, get a little f, then we can use this formula in reverse, right? So for example, it is useful if the denominator is more complex. It's an irreducible quadratic, right, for example. Right, so then what we do is we complete the square, right? So you have s plus a. So really you have something. So if this s plus a, if it had been s, then you have just s squared plus b, and we could work with that. We know how to do those are going to be sines and cosines, right? So that's what we're going to do. So for example, let's look at this guy over here. So we complete the square in the denominator. It's this thing, right? I mean, this is irreducible, correct? It has complex roots, right? So we can write it like this. So you have s plus 2 squared. Now, if s plus 2, if instead of s plus 2 we had s, well, that would be good. We would just have 1 over s squared plus 4, right? We know how to handle that, right? I mean, if we had 1 over s squared plus 4, if this s plus 2 was just s, right? Then, well, okay, you have to, if you want to apply the table, I mean, that's going to be sine because there's no s on top. So because 4 is 2 squared, I need a 2 here, right? The omega had better be 2, so I need to pull out a half, right? That's why there's a half here. Now I can apply the table, so that's sine of 2t, so I have 1/2 sine of 2t. Now that's not the thing that I'm looking at, right? I have 1 over this, not 1 over s squared plus 4, right? But we put it together with the shifting property. So this thing, I mean, this is equal to this, right? And now this is my f of s plus 2, right? That's over here, right? And capital F of s is this thing, right? So I take this and I multiply it by e to the minus 2t, and that's what this guy is, right? So that's using the shifting property. So first shifting property. There's going to be also like a second shifting property if we're doing the same thing on the on the s side, right? Shifting, shifting in t versus this is shifting in s. All right, this one is slightly simpler. All right, now one final remark. You know, I talked about this before. So most of the time, we're going to be the 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 uh, the, the Laplace transform is going to be something like this, where you have some rational function. Maybe there's going to be some exponentials in there, but yeah, a lot of times it looks like this. So you have polynomial over a polynomial. Now, if this was a Laplace transform of an exponential order function, we said then this thing goes to 0. That means that it's a proper rational function, right? If you remember what this meant. And what that says is that well, you can always apply uh, you know, partial fractions, but if you don't have a proper rational function, you have to first divide, and then you have some polynomial, and we don't know how to handle the polynomial at all, and you know it will, the polynomial comes up with some weird things. We're going to look a little bit later at the delta function, but those are not going to be, definitely not exponential order functions, right? But for exponential order functions, for sort of the type of functions that you really think about, things that are continuous, or maybe jump discontinuities and go off to infinity, but not too fast, then what we have is that those Laplace transforms are going to be proper rational functions if they're rational functions, and then what it says is that partial fractions will always just work, right, without any division, and and we can easily just use the table before, right? So as long as you have a proper rational function, everything is great, and those are precisely the kind of things that you'll get for exponential order functions. All right. Now, downside is, well, there's always a downside, right? Well, so it says that it's just with partial fractions, as long as you have something that's a polynomial, or maybe with like a couple of exponentials thrown in, if you can factor them out, you can always basically do this do this sort of thing. With the exponentials, you have to do the other shifting property, but it's in general, you're essentially looking at these rational functions. Now, partial fractions, if you remember, the downside is you have to basically factor the denominator, which is hard, or it can be hard. And if the denominator is really complicated, it can be hard. If it's not too complicated, then it's not too bad, as we saw, right? But so that's kind of the hard bit of the problem, then, is factoring the denominator, right? But once you have the denominator factored, it's just a bunch of algebra, really, right? And looking at the table. So, all right. So if you notice, I mean, so far, we started the section was talking about differential equations. We haven't really gotten to any differential equations, so that's what we're going to get to next. In the next section, we're going to look at how does Laplace interact with derivatives, and therefore how do differential equations transform, and so that we can actually solve differential equations with this stuff, right? I mean, so it's not just we're just not defining something with no use, right? Okay, so that's what we're gonna do next time. We're actually gonna try to apply it to differential equations. All right, see you then.